on Catalyst. Wild weather getting wilder. And capturing the underwater world like never before.
Heat waves that kill tens of thousands. Apocalyptic floods. Blizzards in the Middle East. How is it that a slightly warmer atmosphere can create weather that swings from one extreme to the next? From lazy jet streams to baking soils, in this report we explain the mechanisms behind some of the most catastrophic events of the decade. Understanding exactly how a warmer world drives weather wild is crucial to predicting just how bumpy a ride we're in for. In 2003, a heat wave settled over Europe. But this was no ordinary heat wave. By the time it was over, more than 40,000 people were dead.
So 2003 was remarkable in many aspects. It was far warmer than ever before, 2 to 5 degrees on average over the whole summer.
It was likely the hottest weather event in Europe in 500 years. Yet just 7 years later, an even more intense heat wave hit Russia, setting the country on fire. Summer temperatures reached up to 13 degrees above average, and the death toll from heat stress and respiratory illness was estimated at more than 50,000.
It was much larger in spatial extent, so it covered almost 2 million square kilometers. Really, we're not that used to such extremely hot summers, so it is surprising to see a clustering of such strong events. It wasn't only the two, there were 3 other very warm summers within the same decade.
Global average temperatures have only increased by 0.8 of a degree Celsius. One would think that this would just lead to slightly warmer summers, but actually it's greatly increasing the chances of extremely hot weather. This past year in Australia, we've seen plenty of heat. At the Bureau of Meteorology, forecasters have been watching record after record tumble.
January was the hottest month on record, the summer was the hottest on record. And the sea surface temperatures around Australia were the hottest on record. We had temperatures in Bass Strait, south of Melbourne and south of Adelaide, up to 6 degrees above average. But in terms of heat waves, what we find is the elevated ocean temperatures reduce the amount of cold outbreaks we get. And particularly during April, we had a prolonged heat wave with very hot nighttime temperatures, and those sustained nighttime temperatures are indicative of warmer waters to the south of Australia, and that's what we saw.
Although an exceptional year, it's not outside the range of what's now considered normal. If you plot temperature records, they fall in a typical bell curve pattern, with the majority only a small deviation from the average, and the outliers representing extreme hot or cold events. With a 0.8 degree rise in temperature, a much larger portion now sits in the warmer than average section. And hot to extremely hot days are far more frequent.
Suddenly you've actually doubled the frequency of those events, and in Australia's case up to 5 times an increase in the frequency of extreme heat compared to the middle of last century. And that has all sorts of implications. Just in January alone, we did about 1,600 spot fire forecasts, so that's a very detailed forecast for the firefighters, and that's the equivalent of the last several years.
Worldwide, heat waves have been increasing in duration and frequency since the 1950s.
What we thought as kind of exceptional in the past has really started to become the norm.
But even in the context of global warming, the European and Russian heat waves are way off the charts. Is this just natural variability, or is something else happening to make temperatures soar? The Swiss Institute of Technology is a world leader in climate modelling. Here, Dr. Eric Fisher has focused intensive research on the causes of the 2003 scorcher and other recent severe heat waves in Europe.
It was mainly the key factor is always the atmospheric circulation. So there needs to be a high pressure system in place to get such an extreme heat wave.
But there was something else they all had in common: dry soils.
All of them were actually preceded by very dry conditions in the spring. So we think that these conditions were already preconditioning the later heat wave.
Low rainfall in the spring months led to an early and rapid loss of soil moisture. And dry soils can be a double whammy on an evolving heat wave. When the sun's rays hit the land surface, a lot of their energy goes into evaporating moisture from the soil and from plants as they transpire. But when soils dry out and plants stop transpiring, the sun's energy is no longer channeled into that process. Instead, it's free to heat the surface. The result is a jump in temperatures. It was dry soils that turned the European heat wave of 2003 into a deadly scorcher.
With the very same conditions in the atmosphere, but wet soils rather than dry soils, the 2003 summer would have still been a very warm summer, but much less extreme, with much less devastating impacts.
An early snowmelt and dry soils also amplified the Russian heat wave of 2010. What's disturbing is that many regions appear to be trending to patterns of lower rainfall in winter and spring months, making those areas more prone to mega heat waves.
Europe and Central Europe was always thought to be always humid, basically. So it was a surprise that in that event, more dry conditions was actually enough to amplify the heat wave, something that usually only occurs over dry regions such as the Mediterranean or the central US or Australia, for instance.
From where I'm standing, heat waves seem a long, long way away. So do dry soils. And although this summer has been the hottest on record, it's also had some torrential downpours. So how is it that it can be getting hotter, drier and wetter at the same time? It's simple physics. When air gets warmer, it can carry more water vapour, much more. So any small rise in temperatures should lead to considerably more moisture being sucked from the Earth's surface. But what goes up must eventually come down.
Rainfall, as we all know from personal experience, is really spotty. I mean, it can be raining, in your suburb and next door not raining at all. And so that spatial sort of graininess of rainfall makes it an incredibly hard thing to measure, and in particular to measure over large areas accurately.
To find out if a warmer climate is cranking up the water cycle, scientists have been searching for clues in the restless, churning oceans.
Most of the evaporation and most of the rainfall in the world actually cycles through the ocean surface, not through the land. Because it covers 75% of the Earth, most of the action's actually happening over the ocean.
Every time rain falls or water evaporates from the sea, the surface salinity changes.
When we look at the ocean salinity field right now, we see this beautiful reflection of what happens in the atmosphere. So the places that are very rainy, say the tropics, where there's a large amount of rainfall all the time, the surface salinity field is very fresh. When we go to the parts of the atmosphere where we find deserts on land, there are desert equivalents over the ocean where evaporation dominates, and that's where we find the surface of the ocean is very, very salty.
Keeping track of how salty seas change, more than 3,000 ocean robots called Argo floats have been bobbing about on global currents, beaming back data over time. The oceans are always mixing, so results are smoothed out instead of patchy like land records. Argo data and long-term records from research vessels reveal an unmistakable trend.
Over the last 50 years, that contrast has gone up quite markedly. So, for instance, the Atlantic Ocean is becoming saltier and saltier and saltier, and the Pacific is becoming fresher and fresher. Essentially translates to the fact that the wet areas have become wetter and the dry areas have become drier.
The big surprise is how fast the change is occurring. For every degree rise in air temperature, the water cycle is intensifying by 7%. That's double climate model predictions.
The intensity of the storms are likely to go up because the moisture in the atmosphere is actually the feeder energy stock that drives storms. And we expect droughts and floods to amplify as well.
And that's what's happening. These days, when it rains, it really pours. In January 2011, Toowoomba set a terrifying example of what can happen when too much water comes down too fast.
We are moving!
The town experienced an inland tsunami as 100 millimetres of rain fell in under an hour.
You get very intense rainfall events in a very short period of time, like you did in Toowoomba. The soil just can't absorb that much water, and then you do start getting these very large inland flooding events.
By studying over 8,000 rain gauges across the world, Australian scientists have confirmed that extreme rainfall events have also been intensifying. That means we're getting more water from a big storm than we would have 30 or 40 years ago. Around 7% more per degree rise in temperature.
At its peak, a wall of water at least 4 metres.
It surprised us all, I have to say, that we got the answer we expected. So, because usually in science you don't always end up with the answer you expect. So to sort of see this coming out consistently in the data was somewhat of a surprise.
We're already starting to detect and see big changes in the extreme events, and we've only really warmed the Earth by 0.8 of a degree. If we were to warm the Earth by 3 or 4 degrees, the changes in the hydrological cycle could be near 30%. I mean, that's just a huge change, and it's very hard for us to imagine.
Well, that explains heat waves and floods, but it doesn't take a genius to work out that higher temperatures don't set the scene for blizzards. In marked contrast to a sweltering March last year, this year the US suffered through nail-biting cold. In fact, much of the Northern Hemisphere was buried under record-breaking snowfalls. How can global warming possibly explain that? To understand how, you need to consider the basic drivers of climate. As the sun heats the Earth unevenly, it sets up temperature gradients on many different scales. These create the winds and currents that influence weather.
All the ocean currents are driven by basically the temperature gradient between the equator and the pole, and it's the same in the atmosphere.
The atmospheric gradient between the tropics and the poles creates the major westerly winds called jet streams. Wind rushes down a slope from a warm, puffed-up atmosphere to a cold, compressed atmosphere.
The stronger that gradient, the stronger the force that wind is being pulled by, if you will. And then because the Earth is spinning, instead of flowing directly from the south to the north, it actually gets turned to the right by the spinning of the Earth.
These fast-moving wavy winds encircle the northern and southern hemispheres and mark the divide between cold polar air and warm tropical air.
They swing north and they swing south, and the weather that you experience is completely related to where you are relative to one of these waves.
But what happens when you mess with the temperature gradient? It's a hotly debated topic, and right now we're running an extraordinary real-world experiment by turning up the thermostat in the Arctic.
It's hard to get your mind around how fast the Arctic is changing. It's really mind-boggling, even to someone like me who's been studying it for decades now.
The Arctic is warming faster than anywhere on Earth. largely to do with the feedback effect of melting sea ice. White, bright ice bounces the sun's rays back into space before they have a chance to warm the surface. But when a small rise in temperature melts some of the ice, the dark ocean below is exposed. This absorbs almost all the sun's energy and heats up, causing more ice to melt, leading to more warming, and so on.
What we're seeing is the Arctic sea ice disappearing at just an amazing rate. This is the ice that's floating on top of the Arctic Ocean. This past summer, it was half as big as it was only 30 years ago.
Research by Dr. Jennifer Francis has shown that Arctic summers with a low sea ice extent leads to a gentler atmospheric gradient.
The force that's creating those winds in the jet stream is getting weaker as well.
Like fast-flowing mountain rivers meander when they slowly cross the coastal plain, Jennifer predicted a weaker, slower jet stream would display a much wavier pattern.
We were able to determine that, in fact, these waves are actually getting larger in the north-south direction, which we know through weather theory that those waves then tend to move more slowly from west to east.
And a lazy, meandering jet stream can have an extraordinary effect on weather.
A big dip south, for example, will allow that cold air from the Arctic to plunge farther south. And conversely, if you have a big swing northward in one of what we call a ridge, then that allows the warm tropical air to extend farther northward. So in both of these cases, we tend to get more unusual weather patterns setting up.
That's exactly what happened when frigid Arctic weather plunged into Europe and southeastern US this March, bringing record snowfalls and leading many to wonder what happened to global warming. The year before, the US was caught in a jet stream upswing. Unprecedented heat smashed over 1,000 temperature records and set the scene for a staggering drought and massive agricultural losses. This decade, the Northern Hemisphere has seen some catastrophic results from a highly deformed jet stream. While a big stagnant high settled over Russia in 2010, cold air from Siberia plunged into Pakistan, colliding with warm, wet air from the Bay of Bengal. As Russia burned, Pakistan drowned under a deluge that lasted nearly 2 months.
As the jet stream takes on this wavier character, what this means is that the weather that you're experiencing in your location is going to stick around longer. It's going to feel like those weather conditions just won't give up and bring something else. It feels like it's stuck.
How jet streams are being affected by a warming Arctic is still highly unpredictable, with many other interactions affecting their speed and movement. But one thing's certain: we'd better get used to wacky weather.
When we talk about climate change in the future of 1, 2, 3 degrees, it's actually hard to imagine.
It's going to be a difficult next few decades, I think.
When it comes to extreme weather, the connection is pretty clear. The warmer the world, the wilder it gets. And with the speed that emissions still enter the atmosphere, we're right on track for an unrecognisable future.